Okay, let us see the next point. This is important. The gravitational potential energy. Okay, now what is that? So you might say, suppose this is an object, it is lifted up against the gravitational force. Then we know from work energy and power that work done against a conservative force gets stored as what? The potential energy. It increases the potential energy. So a potential energy on Earth's surface, if we consider it to be 0, then potential energy at height h would be equal to what? mgh, right? So we know this from work energy and power. But there, what did we consider? We considered that g remains constant, right? G remains constant. That means it is applicable for very small heights. Okay, 1 kilometer, 2 kilometer, 50 kilometer, etc. up to 100 kilometer. But then we know that g does not remain constant. Okay, you have g at height h is equal to what? G multiplied by 1 minus 2h upon r. So this formula for potential energy is not quite correct, right? It is applicable for very small heights. Okay, then you can find out change in potential energy, work done, etc, etc. Is this thing clear? Yes, no? Okay, so now see, now we'll derive the formula for gravitational potential energy. Okay, so now suppose this is earth, and you have this mass m, and the gravitational force is pulling this mass towards the center of earth. And now suppose we want to displace it from this much distance r1 to distance r2. So the gravitational force is given by what? F is equal to minus of g times mass of earth times this mass m divided by r square. Okay, whatever is r. Then I want to displace it, so I need to exert some external force that will be opposite to that of what? The gravitational force, right? So gravitational force is negative, means it is attractive force. Okay, so work done against gravity or gravitational force to displace this object, okay, of mass m from distance r to r plus dr. What will be the work done? So work done for this small displacement would be equal to what? The externally applied force, which is gmm divided by r square, same in magnitude as that of the gravitational force, okay, multiplied by this small distance, okay, dr. So I am displacing it, let's say from here to here, okay, that is dr, displacement is dr. What's the work done? Gmm upon r square multiplied by dr. Then suppose I want to displace it from some position from distance r1 to distance r2, okay, from the center of earth. Then what do I need to do? So I need to integrate this work to get the total work, okay. So work done to displace it from position r1 to position r2. So work done would be equal to just integration of work done to displace it by displacement dr. So integration from r1 to r2 of this thing, and out of this g times mm is a constant, okay, g is universal gravitational constant, m is mass of earth, small m is mass of the object, all of them are constants. So we can move these things outside, right? So gmm we move outside. So what remains is integration of 1 upon r square dr, which you can say it's integration of r raised to minus 2 times dr, okay, and you have this formula of integration of r raised to n dr, okay, I wrote dx here, so variable and this thing should be same, right? So it is function of r, integration of r raised to n dr is equal to r raised to n plus 1 divided by n plus 1, okay. So if units are given, limits are given, then within the proper limits, okay. So this thing we know. What is our n here? N is equal to minus 2. So what will be the integration? R raised to minus 2 plus 1 divided by minus 2 plus 1. Okay, so that is r raised to minus 1 upon minus 1, and you can rewrite this thing as, you can take that r raised to minus 1 in denominator, so it becomes 1 by r, okay, and this negative sign will be there from some r1 to r2, right? and then you put this R1 and R2, you substitute R1 and R2, you can take negative sign outside, so minus of GMM, okay, 1 by R from R1 to R2. If you substitute R1 and R2, that means lower limit and upper limit, so you get minus of GMM multiplied by 1 upon R2 minus 1 upon R1. Is this thing clear, everyone, up to this point? Right. So now suppose you displace it from infinity to R. Suppose you displace that object from infinity to R. So starting position is infinity and final position, okay, it is at distance R. Position can be anywhere, but it is at distance R away from the center of earth. Then you substitute R1 equals to what? Infinity, and R2 is equal to R. Just substitute that. So R2 is equal to R, R1 is equal to infinity. Okay. So now we know that this work done against a conservative force gets stored as what? Potential energy. Right. Um, work done against the conservative force increases the potential energy of the object. So this work done can be written as what? The work done can be written as change in potential energy, U at R2 minus U at R1, right? So U at R2 minus U at R1 is minus of GMM multiplied by 1 upon R2 minus 1 upon R1, okay? And then we substitute R1 equals to infinity, so this U at R1 becomes U at infinity, and R2 equals to R, R2 equals to R, okay? Then what do we get? U at R, that means potential energy of these two objects, that means earth and the other object, when separation between them is R, is U at R, minus potential energy when the separation between them is infinity, okay. So this difference, potential energy difference, is equal to minus of GMM multiplied by 1 by R2, which is 1 by R, right, minus 1 by R1, so that is 1 by infinity. 1 by infinity is 0, therefore you get this thing, the potential energy difference is equal to minus of GMM divided by R, okay. You get minus of GMM divided by R, and then what we do is, for simplicity we just consider, just say that potential energy at infinity is equal to 0, and this is just a convention, right? So once again, okay, what we can find out, what we can measure, so we can measure the difference in potential energy and not the actual potential energy, okay. So we studied this in work energy and power also, and it will keep on coming, okay. So what can we measure is the difference in potential energy and not the actual potential energy, and that's why what we do is, for simplicity we choose, okay, we choose the potential energy at infinity is equal to 0, right? So this is a choice. So then if we substitute that here, then what do we get? We get U at R, potential energy when the separation between these two objects is R, is minus of GMM divided by R, okay, minus of GMM divided by R. Is this thing clear, everyone? Right? Now this convention, so this choice has been made already, so we just need to remember this formula. So potential energy is minus of GMM divided by R, okay. Alright, so we studied potential energy. After that, so now this R can be written as, if we take the context of this chapter, we write R is equal to, small r is equal to R plus H. That means we have earth like this, and this is radius of earth, capital R is radius of earth, right, and our object is at some height h, okay, from the center, sorry, from the surface of earth. Then the separation between Earth's center, and that object can be written as small r, which is equal to r plus h. We can always do that. So small r can be written as r plus h. So this is potential energy at height h above the Earth's surface, and this is the correct formula now. Okay. If h is comparable to r, we should use this formula, right? If h is comparable to r, we should make use of minus of gmm divided by r plus h. Okay. And then if you remember, gm is equal to gr square. Okay, always remember that gm is equal to gr square. All right, how? So we know that g is equal to gm over r square, which implies gm is equal to g times r square. Okay, and similarly you can say gh is equal to gm divided by r plus h square. Therefore, again gm can be also written as gh multiplied by r plus h square. Okay, so just remember gm is equal to gr square, small g into r square. Okay, capital G times m is g times small g times r square, and it is g at height h multiplied by r plus h square. Okay, this is very handy. Remember this thing. Okay, this thing is clear, everyone? All right. So in place of this gm, we substitute gh multiplied by r plus h square. When we substitute that, okay, one of this r plus h will get cancelled out with r plus h in the denominator, and what remains is gh multiplied by m into r plus h. Okay, so gh multiplied by m into r plus h. This is potential energy at height h. This thing is clear. All right, then okay, good. Then now let's talk about the escape speed. Okay, escape speed. So suppose you have this rocket, or suppose you have somebody, okay, and you want to send, suppose you have some friend or somebody which you don't like, and you want to send him her out of the Earth's gravitational influence, so that it will he will or she will never come back. Okay, suppose there is some person in your life and you hate that person, and you want to send that person somewhere that he or she never comes back. Then with what speed you must throw? Yeah, some relative. Okay, with what speed you must throw that person so that he or she will never come back. So that speed is known as the escape speed. So the person will escape Earth's gravitational bound. Okay, so let's check what's that speed. So the speed with which a body must be thrown, it can be any body, to make it escape from Earth's gravity. Okay, so the potential energy of object at height r, we know it is minus of gmm divided by r, right? So kinetic energy, we know it is half of mv square. And see, now the object never comes back means it goes to infinity. That body goes to the infinity. From infinity it won't be able to come back. Okay, so what we can say is the total energy remains conserved. So from law of conservation of energy, the sum of potential energy plus kinetic energy at r, when separation between Earth's center and that body is r, and it is equal to the sum of potential energy and kinetic energy at infinity, right? Sum of potential energy and kinetic energy at infinity. So put the formula for potential energy. Potential energy becomes minus gmm divided by r, right? And then kinetic energy at distance r must be half of m into v square, because we want to find out the speed with which we must throw a body so that it escapes Earth's gravitational bound. Okay, So it is called as escape speed. We denote it by VE. Okay, V suffix E. So potential energy at infinity we consider it to be 0. Kinetic energy at infinity is half of m into V infinity square. So now velocity at infinity, speed at infinity can be anything. Okay, but even if the speed becomes 0 at infinity, we don't care, right? So at least it should reach infinity. Then at infinity, if it has some speed or it doesn't have any speed, we don't care. Okay, right? So at infinity, what should happen? I mean, at infinity, the speed can be considered to be equal to 0, right? You can consider the speed to be equal to 0. It goes to the infinity and stops there. Okay, infinity means very, very large distance. That's it. Okay, the body goes to the infinity, stops there. This thing we can equate it to 0. Then you can just move. Right hand side is 0. Move this thing on right hand side. So half of mv square is equal to gmm divided by r. Okay. Then you can cancel out m and m. Move 2 on that side. So we get v square is equal to 2 times gm divided by r. V square is 2 times gm divided by r. And therefore what is v? V is root of 2 gm divided by r. Okay, root of 2 gm divided by r. And what is that? So now if you take, okay, so v is equal to square root of 2 times gm divided by r. Is it clear up to this point? Right? Okay, good. So what is this r? Small r, small r is equal to r plus h. And then as we discussed earlier, that we can always substitute gm is equal to, we can always substitute gm is equal to gh multiplied by r square. Okay, capital Gm is equal to gh multiplied by small r square. We can always do that. We can always substitute that. So let's substitute it over here. So what do we get? So if you substitute it over here, so then you have gh multiplied by r square. One of the r from that square gets cancelled out, and you have v is equal to root of 2 gh times r. Okay, 2 gh times r. Okay, so the small r is equal to what? R plus h, right? So you have to remember this formula as well as this formula, both of these formulas. And then what will happen on Earth's surface? So on Earth's surface, you can take h to be equal to 0, right? Just replace the small r by capital R. So you get VE is equal to square root of 2gm divided by capital R, and it is equal to another formula, square root of 2 times g. G is acceleration due to gravity on Earth's surface into r, capital R, right? The small r will become capital R on Earth's surface. So this is clear. Yes, no? Okay. And then the person that you don't like, you will need to throw that person with a speed of 11.2 kilometers per second from the center of surface of Earth. Okay, you will need to throw that person with the speed of 11.2 kilometers per second from the surface of Earth, and it is almost impossible for us, right? Okay, so what is this thing? This is the escape speed on the Earth surface. Okay, you want to throw something from Earth surface and so that it will never come back. So speed must be 11.2 kilometers per second. How do we know? We can just substitute values over here. G is equal to 9.8 and R is equal to 6400 kilometers. Then we get this value. Okay. Okay, good. So we need to remember this and this formula, root of 2 gm over r, and it's also equal to square root of 2 gr, right? Now depending upon the problem, it can be small r or capital R. Okay, right? And small r is just capital R plus H. Okay, alright. So then we define a term called as gravitational potential. We discussed gravitational potential energy. Okay, and related to that there is a term called as gravitational potential. So it is work done to bring a mass from infinity to r. So what is gravitational potential at any position in space? So it is work done to bring a mass small m, let's say, from infinity to that position, okay, divided by the mass. Okay, so then what would be the gravitational potential of earth? Okay, gravitational potential of earth at some distance r from the center of earth. So it is by definition work done to bring a mass m from infinity to r, okay, divided by that mass. So we know that how much is the work done to bring an object from infinity to r? It is minus of gmm divided by r, right? And divide that work by small m, that is mass of the object. So this m and m gets cancelled out. So gravitational potential due to earth, okay, gravitational potential of earth at distance r from the center of earth is given by this formula: V is equal to minus of gm over r, and as we discussed, gm can be replaced as gh into r square. So we can just write the gravitational potential as minus of gh into r. So is this thing clear, everyone? Right. Okay, very good. And then now there is some relation between force and potential energy that we had discussed in work energy and power. So what is that relation? So we know that force is what? Negative gradient of potential energy, right? Not potential, potential energy. So force is negative gradient minus of du by dr. Okay, we know this from work energy and power. So you can just substitute that u is equal to minus of gmm over r. So this negative negative becomes positive. Okay, you can move gmm outside, then you have d by dr of 1 by r, and that is minus 1 upon r square. Okay, derivative of 1 upon r with respect to r is minus 1 upon r square. So once again what do you get? You get back the gravitational force, right? So this is the relation between a conservative force and potential energy. We know this from work energy and power. So here we have just verified it for the case of gravitational force. This thing is clear, everyone? Okay, good. And then okay, and then now you divide both sides of this equation by small m. If you divide both sides by small m, what do you get? So force upon mass is called as gravitational field, okay, that is small g we can say, and it is equal to minus of d by dr of u upon m. So if you divide u by m, what do you get? You get minus of gm by r, and that is v, right? So if you divide u by m, what is u? Minus of gmm upon r. If you divide that by m, so m gets cancelled, what do you get? You get minus of gm divided by r. So minus of gm divided by r is the gravitational potential. We just saw minus of gm upon r is the gravitational potential. So therefore you have gravitational field is equal to minus of dv by dr. This is a problem from NEET 2023. Two bodies of mass small m and 9 times m are placed at distance capital R. The gravitational potential on the line joining the bodies where the gravitational field equals 0 will be. Tell me. So you have two bodies. This has small m mass, and the other body has mass equal to 9m. So suppose this is some point P, it is at some distance, let's say x, where the field becomes 0. Okay, gravitational field becomes 0. Okay, so then what will be that distance? How can we find it? Tell me. So gravitational field due to this mass m would be directed in this direction. Gravitational field due to the other mass would be directed in the other direction, right? So both fields, if they are equal and opposite, both fields, if they are equal and opposite, then we can say the total field is equal to 0. Yes, no? Okay, good. So we can find out the distance. So we can say m1, what is the field? G times m, okay, upon r square. So here for this mass, it should be g times small m upon x square, right? So we can say g of mass m1 must be equal to g of mass m2. Okay, we'll put the values of m1 and m2. m1 is m and m2 is equal to what? 9m, right? So that means g times m1, which is m, divided by x square must be equal to what? G times 9m, okay, 9 times m divided by, this is small m, okay, r minus x square. What is distance of this point from this mass? If this total distance is r, this distance is x, then the remaining distance is r minus x, right? So then you can cancel out g. Okay, you can cancel out mass and this mass. So 9 times x square is equal to r minus x square. Take square root. So 3x is equal to r minus x, and that means 4x is equal to r. So x is equal to r by 4. Okay, you got that, right? Okay, and after that, so you got x equal to r by 4. Then calculate the gravitational potential. Okay, so there would be some gravitational potential due to first mass and some gravitational potential due to second mass. So total potential would be potential due to first mass plus potential due to second mass. That is, what is potential due to first mass? Minus of gm divided by its distance x. Okay, then you have plus potential due to the second mass is minus of gm divided by r minus x. Then put the values. Okay, g times, this is 9m, no, this is 9m. So you have minus of gm divided by what is x? X is r by 4. Okay, so r by 4. Take that take that 4 in the numerator, and then you have minus of 9 g times m divided by r minus x. So r minus r by 4 is 3r by 4. 3r divided by 4. Okay, so then this 9 by 3 is 3. Okay, negative sign you can take common. So you have, okay, this will be minus 4 times gm over r, and this thing would be equal to minus of 12 times gm over r, right? So minus 16 gm over r, that should be the answer. Option C, right? Yes, no? See, this thing is equal to minus of 4 gm over r, and you have minus of this thing becomes what? 3, and that 4 goes to the numerator, minus of 12 gm over R. So minus 12 minus 4 is minus 16 gm over R, g times m over R. This is the answer, right? It's option C. So now somebody said option A, right? That is not correct. You don't have to subtract the gravitational potential from one another. Okay, so this is a scalar quantity and you just need to add it up. Is this thing clear? Right? So answer is option C. Okay, good. So this one was from NEET 2023. Okay, quite a good question and slightly lengthy also, right? But not difficult. Okay, so let's see next question. A body of mass 60 grams experiences, can you see this? This is very faint. You can read this, no? A body of mass 60 grams experiences a gravitational force of 3 Newton when placed at a particular point. The magnitude of gravitational field intensity at that point is. Okay, tell me. This is from NEET 2022. Okay, so body of mass 60 gram experiences some force. This is given. We know that force is equal to mass of the body multiplied by gravitational field. This is very simple. Option A. Let's check. So force is what? 3 Newton. Okay, force is 3 Newton. So that force is equal to mass of the body is 60 grams. 60 multiplied by 10 raised to minus 3 multiplied by g. And we want g. So let's take these things on other side. So g is equal to this 10 raised to minus 3 will become 10 raised to plus 3. So 3 times 10 raised to 3 divided by 60. So 3 by 6 means 1 by 2. Okay, so this thing will be 1 by 20 because the 0 is there. So 1000 divided by 20, yeah, 50. Okay, 50 Newton per kg. The answer is option A. Very good. So this one is clear, very simple. Right, good. Let's see next one. I think I have arranged it in descending order. Okay, NEET 2023, 2022, 2019. Alright, the work done to raise a mass m from the surface of earth to height h, which is equal to the radius of earth is. Tell me. Work done is equal to work done is just equal to change in potential energy, u at R2 you can say minus u at R1. Okay, u at height h minus u on the surface of earth. Okay, so that is, what is u at height h? So gmm divided by r plus h minus gmm upon r, right? On surface of earth it is gmm upon r, but there is negative sign too. Okay, minus u itself is minus of gmm over r. We should not forget this negative sign, right? So then you can take gmm common. Okay, and let's substitute what is h first. H is equal to what? Radius of earth only. So this is minus of gmm divided by r plus h. So that is 2r plus gmm divided by r. And then you can take gmm, g times capital M small m upon r common. Then you have minus 1 by 2 plus 1. So 1 minus 1 by 2 is 1 by 2 only. So the answer is, work done is equal to gmm divided by 2r. Is it there? You can always substitute then. Okay, it is not there in this form. So you can always substitute Gm is equal to what? Gr square. Put that. Okay, because options are given in this way. Okay, put it over there. So Gm is equal to Gr square, and then therefore you get W is equal to what? Gr square times m upon 2r means half of mgr. This is the answer, right? It's option D. This one is clear. Okay, everyone. Okay, very good. Let's see next one. At what height from the surface of Earth the gravitational potential and the value of G are? This thing is gravitational potential and this is value of G respectively. Take the radius of Earth as 6400 kilometers. Okay. So then V is equal to, let's use the formula. So you have minus of Gm divided by R plus H, right? But we should not use this one because acceleration due to gravity is given, right? So you can always substitute Gm is equal to what? Gh times R plus H square. Okay, and therefore you get what? Gh multiplied by R plus H. Okay, yes, no? And we just want the height. Okay, is this thing clear? You have the formula for gravitational potential, which is minus of Gm upon R, small r. That small r is equal to capital R plus H. And because they have given the value of G at that height, so we should not use this formula. Okay, we should write the formula in terms of acceleration due to gravity, right? This one is clear? Yes, no? All right, so put the values. What's given? This is 6. Okay, gravitational potential is minus 5.4 multiplied by 10 raised to 7, and it is R plus H. Okay, so let's keep it R plus H for now, and then you can move this 6 on other side. So 5.4 divided by 6 is how much? 0.9. Okay, so 0.9 into 10 raised to 7 means 9 multiplied by 10 raised to 6, and radius of Earth is equal to 6.4 multiplied by 10 raised to 6, right? 6400 kilometers. 6400 kilometers means 6.4 into 10 raised to 6 plus H is equal to this thing, and therefore what is H? H is 9 minus 6.4 multiplied by 10 raised to 6. Okay, so I am taking this thing on other side. 9 minus 6.4 into 10 raised to 6 in meters. So 9 minus 6.4 is 2.6. 2.6 into 10 raised to 6 meters, or it is 2600 kilometers, right? Because options are given in kilometers. This thing is clear, everyone? Right, good. So now see, you could directly write down this formula, because for potential energy we have studied potential energy is equal to what? Minus of Gmm divided by R, or Gmm divided by small r, which is capital R plus H, or it is equal to minus of Gh multiplied, sorry, minus of mgh multiplied by R plus H. And what is V? V is just U divided by m. Okay, V, the gravitational potential, is potential energy divided by mass. So if you remove m, you can write down this formula, minus of gh into r plus h, right? Or you can just remember this formula for gravitational potential. Okay, good. Then let's see next one. A body of mass m is taken from Earth's surface to height equal to twice the radius r of the Earth. The change in potential energy of the body will be. So again, this is simple. Okay, so change in potential energy delta PE is equal to final potential energy minus GMM divided by, so body is taken from what? Taken from Earth's surface. Okay, so final potential energy, so say u at height h minus u on the Earth's surface, so that is minus GMM divided by r plus h minus GMM divided by r, right? This is potential energy at height h, this is potential energy on Earth's surface. Okay, and that is equal to minus GMM, okay, minus GMM divided by, this is 2r plus GMM, not 2r. How much is the distance? H is equal to, h itself is 2r. Okay, so h is 2r. So this thing would be equal to what? Minus GMM divided by 3r plus GMM divided by r, right? So option D, let's check. What is this thing? 2 by 3, right? GMM upon r, you can take common. So it is 1 minus 1 by 3. So it's 2 by 3. Okay, 2 by 3 GMM over r, and GMM over r is equal to mgr. We know that. Okay, so therefore it is 2 by 3 mgr. It is option D, right? So this thing is clear. Okay, so then see, suppose you move a body from some position r1 to position r2. What is change in potential energy? Change in potential energy is equal to minus of GMM divided by r2 minus GMM divided by r1. Okay, so then this minus minus becomes plus. Okay, and then you can take GMM common. It's 1 by r1 minus 1 by r2, right? 1 by r1 minus 1 by r2. Okay, so you can always make use of this formula directly. Okay, so for an example, in the last problem, what we could do is, so change in potential energy when we move a body from height r1 to r2. Okay, so that is, again, this thing also can be simplified. So GMM, this will be r2 minus r1 divided by r1 r2. Okay, but I guess in place of this, this formula is, this one is sufficient, right? So in case of last problem, if we make use of this one, delta PE, it's equal to, what's that? GMM, and what is R2? So R2 is equal to R plus H, so that is 3R. So this is 3R minus 3R minus R1 is R divided by R1 R2 would be 3R square, right? So then 3R minus R is 2R, 2R divided by 3R square means it is 2 by 3R. So it is equal to GMM, okay, multiplied by 2 by 3R, 2 by 3 GMM upon R. Okay, so if you remember this formula, then you can directly put the value, right? So change in potential energy when body is moved from R1 to R2, it's equal to gmm multiplied by R2 minus R1 divided by R1 R2. Okay, this is clear? Yes, no? Just put the values there. Okay, so initial position or initial distance is R1, that is radius of earth. Final is R2, which is R plus H, whatever it is. Okay, all right, good. So we can make use of this formula, right? Let's see this topic, small topic. So there can be a direct question based upon this one. So gravitational potential inside a spherical shell. Okay, inside a spherical shell. Right, so suppose we have the spherical shell and we want to find out its gravitational potential for any interior point. Okay, so now what would be the gravitational potential? So see, we know the gravitational field G is equal to what? It is minus of derivative of gravitational potential. We just saw this. Okay, G is equal to, gravitational field is equal to minus of dV by dr. Okay, gravitational field G is equal to minus of dV by dr. So what is the field inside? Tell me. Gravitational field inside a spherical shell, G is equal to 0. Very good. So G is equal to 0 means derivative of V with respect to R is equal to 0 for any interior point, and that means that V must be constant. Okay, V must be constant, right? So suppose radius of this shell is R. Okay, what would be gravitational potential on or at a point on the surface of the shell or any outside point? Let's say here, what is gravitational potential? So gravitational potential at some position R, where R is greater than capital R, okay, greater than or equal to capital R, would be equal to, so V would be equal to minus of Gm divided by R, right? This thing we know. Okay, if m is the mass of the shell, then its gravitational potential for a point which is outside, it would be equal to minus of Gm upon R. Okay, and then what would be on the surface of shell? So on surface of shell, V would be equal to minus of Gm divided by R, right? Then the small r just becomes equal to the radius of shell. Now therefore, what would be the gravitational potential in the interior also? In the interior region too, the gravitational potential will be minus of Gm upon R, because when you move from shell, okay, from the surface of shell towards interior region, what happens is the potential should not change. V should be constant. V is constant, that's why field is 0. Okay, if potential changes, then what would happen? There would be some field. Is this thing clear? On surface and in the interior region, okay, in interior region, interior point 2, V is constant, means V is minus Gm over R. Is this thing clear to everyone? Yes, no? right, everyone? Okay, very good. So if you have a spherical shell, then the potential for any interior point would be minus of gm over r, radius of the shell. Okay, so now let's see that question. So particle of mass m is situated at the center of a spherical shell of same mass and radius a. The magnitude of gravitational potential, okay, at a point situated at a by 2 distance from the center will be. Okay, so you have a shell like this, and also at the center of shell there is a particle having mass m. Okay, mass of the shell is also m, and its radius is, they say, it is a. So then the magnitude of gravitational potential at a point situated at a by 2 distance from the center. Okay, so you want the potential at distance a by 2, let's say at this point, point P, which is at distance of a by 2, right? This much distance is a by 2. So tell me, what should we do? Okay, so potential there would be equal to potential due to shell plus potential of this mass, okay, point mass m, right? So potential due to shell is constant over uh, the whole interior region. That means anywhere at any point in the interior, potential due to shell, we just saw it's a constant, and it is minus of gm divided by radius of the shell. So that is a, okay, plus potential due to this mass. If you have small mass, a point size mass m, then what is potential due to that? It is minus gm divided by the distance, right? So what is the distance? So minus gm divided by the distance of that point. So distance is a by 2. Okay, so this thing becomes minus 2 gm over a, and you have minus gm over a. So the answer is minus 3 gm over a. So this is the answer. Okay, so answer is point option C here, but they should say that it's negative, right? So this thing is clear, everyone? Okay, good. So if there is 3 gm over a and minus 3 gm over a, then which option will you choose? Negative one, right? Okay, yes, no, good. Let's see next one. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. Okay, so it's a nice concept. Black hole is an object whose gravitational field is so strong that even the light cannot escape from the black hole. To what approximate radius would Earth have to be composed to be a black hole? Have to be compressed. Okay, you want to compress Earth and you want to make Earth a black hole so that light will also not escape. So we know that what is the escape velocity? It is square root of 2 gm over r, right? So mass of Earth is given. Okay, then we need to put the values. So this r is not the radius of Earth. Okay, it is now when we compress the Earth, what should happen? The escape speed should become speed of light, 3 into 10 raised to 8. Then what should be the radius of Earth? This is the question. 3 into 10 raised to 8 is equal to square root of 2 gm. So that is 2 times of g is 6.67 into 10 raised to minus 11. Okay, so first of all let's square this one. Okay, let's square this one. So we get V square is equal to 2gm divided by r. Okay, let's move r on other side. So r is equal to 2 times gm divided by V square. And then let's put the values. Okay, so r is equal to 2 times of 6.67 multiplied by 10 raised to minus 11. Okay, m is 6 into 10 raised to 24, and V square is 3 into 10 raised to 8 square of that, right? So then this is 10 raised to minus 11 plus 24, that is 10 raised to 13. 6 times 2 is 12. Okay, we just want order of magnitude. So okay, so this 6 times 2 is 12, that can be approximated to 10. 10 times this 6.67 also we can approximate it to 10, so that becomes 10 square. It becomes 10 square. 10 square divided by, you have 9 multiplied by 10 raised to how much? 16. So this also you approximate it to 10. So this thing is 10 raised to 17. Okay, and in numerator you have 10 raised to 15. So the answer is 10 raised to 15 minus 17 means 10 raised to minus 2 meters. Okay, so it is option C, right, if my calculation is correct. So you need to compress Earth to the radius of 10 raised to minus 2 meters, then it will be a black hole. This thing is clear? Yes, no? Okay, right, good. So you can imagine how dense would be an actual black hole, right? Okay, let's see next question. The radius of a planet is twice the radius of Earth. Both have almost equal average mass densities. Vp and V are escape velocities of the planet and Earth respectively then. Okay, so what's the relation between them? They say that average mass densities of Earth and that planet are equal. Okay, so density of planet is equal to density of Earth, let's say rho only, and radius of the planet is twice the radius of Earth. Okay, so then what would be the escape velocity on the planet? Okay, so let's say escape velocity on planet would be equal to what? Square root of, we can make use of gm divided by r square. Okay, but then we'll need to find out the mass, right? I mean square root of 2 times gm over not gm over r square, gm over r, and we have another formula, let's use that one. So it is root 2 g, okay, multiplied by r, but it will be gp rp because we want to find out escape velocity of that planet. Then why did I use this one? Because I can substitute g is equal to, we know 4 by 3 pi r rho g, right? So in place of r it will be rp, radius of the planet, multiplied by, once again you have radius of the planet. So now radius of planet is equal, density of planet is equal to density of Earth. So this thing can be considered as a constant. Then 4 by 3 pi times 2, that is also constant, right? So everything else is a constant. Okay, we can just say this is rp square, take its square root, so it is rp multiplied by the remaining thing which is constant. It is same for Earth also, right? So that is 8 by 3 pi, okay, 8 by 3 pi times rho times g, okay, pi rho g, right? Then this is Vp. For Earth it will be what? Ve is r multiplied by the same thing, 8 by 3 pi times rho g. And how much is the radius of planet? It is twice, no? Twice the radius of Earth. You can put it over there. 2r. So that means the escape velocity on the planet just equal to 2 times the escape velocity on Earth. Okay, this thing is clear, everyone? Right? Is there a doubt? All right, good. Let us see next one. A particle of mass m is kept at rest at height 3r from the surface of Earth, where r is the radius of Earth and m is the mass of Earth. The minimum speed with which it should be projected so that it does not return back. Okay, it does not return back. That means we just want its escape speed. Okay, so it is square root of 2 gm over r plus h. And what is h? H is equal to 3r. H is equal to 3r. Just put it. So what do we get? 2 times of gm divided by r plus h is r plus 3r, means 4r, and this is 1 by 2 gm over r. Okay, but is it there? It is gm over 2r raised to half. So it's option A, right? This one is clear. Okay, good. Very simple. Tell me this one. A particle of mass m is thrown upward from the surface of Earth with velocity u. Okay, the mass and radius of Earth are respectively m and r. G is gravitational constant and small g is acceleration due to gravity. Okay, the minimum value of u so that the particle does not return back to Earth. Okay, particle is thrown upwards from the surface of Earth. Oh, it is just escape velocity. Tell me, escape velocity from Earth's surface. The minimum velocity so that it does not come back. Yes, it's option B, square root of 2 gm over r. Right? It's very simple. Okay, right. Let's see next one. The Earth is assumed to be a sphere of radius r. A platform is arranged at height r, capital R, from the Earth. The escape velocity of a body from this platform is f times v, where v is escape velocity on surface of Earth. The value of f is, tell me. See, the question is very simple. So escape velocity on Earth's surface is square root of 2 gm over r, and escape velocity at that height h is root 2 gm divided by r plus h. So just put h is equal to r, put it over there. So what do we get? We get root 2 gm divided by r plus r, means 2r. So it is square root of gm over r. That's it. Right. And then you just need to compare these two. Compare this one with this one. So they say that VE is equal to square root of gm over r, and it is f times the escape velocity on Earth. So what is that f? Okay. So VE is equal to f times of v. This is given. You can put the values. So V is root of gm over r, that is equal to f times of root 2 gm over r. The gm over r and gm over r gets cancelled out. Okay, so f times root 2 is equal to 1, means f is equal to 1 upon root 2. Okay, so it's option C. Very, very simple. Right. So I guess Bhanu solved it. Is this thing clear? Yes, no? Okay, it's very simple, right? It's 1 by root 2. All right. Then let's see next one. With what velocity should a particle be projected so that its height becomes equal to radius of Earth? Okay. With what velocity should you throw an object so that its height becomes equal to radius of Earth? This is the question. So what can we say? That if you throw an object and you want it to reach some height, okay, you throw an object, you want it to reach some height, so the speed at that height must be equal to 0, right? Okay, it goes to that height and stops there, so speed must be 0 at that height, right? Yes, no? Okay, so then what can I say? It's energy, kinetic energy plus potential energy on Earth, let's say, right? On Earth you are projecting it, it's equal to potential energy at height h. Okay, there is no kinetic energy at that height, that is half of m, or you can move this potential energy on that side. Okay, so kinetic energy is just equal to u at that height minus u on Earth's surface. Okay, so then we have this formula for u, so it is gmm r2 minus r1 divided by r1 r2. Okay, so this must be kinetic energy, so this is equal to half of mv square, right? So change in potential energy, we have gmm multiplied by r2 minus r1 divided by r1 r2, so we can substitute values there. So what is r2? R2 is equal to r plus h, and what is that? It is r plus height is equal to radius of Earth only, so that is equal to 2r. And what is r1? R1 is equal to r. Okay, so let's substitute that. So this m gets cancelled, and let's put this is gm, so this is half of v square is gm multiplied by 2r minus r, and in denominator you have 2r times r. Okay, this 2 and 2 gets cancelled, so you have v square is equal to, what's that, gm multiplied by this is 2r minus r, no, this is r divided by r square, means 1 by r. Okay, so gm upon r, so v is equal to therefore square root of gm over r. So this is the answer. Okay, so it is option A. This one is clear to everyone? Right? Okay, very good. Let's see this one. For a planet having mass equal to mass of Earth but radius equal to 1/4 of radius of Earth, the escape velocity of the planet will be. Okay, so this is simple. Escape velocity for the planet would be just equal to square root of 2 times g into mass of planet divided by radius of the planet, uh, not square, radius of the planet, right? Square root of 2 gm over r. This is the formula. Okay, so mass of planet is just equal to mass of Earth. This is given. Radius of the planet is equal to 1/4 the radius of Earth. So that is r by 4. Just put it over here. So what do we get? It is equal to square root of 2 times g into m divided by r by 4, and that 4 will go to the numerator. Square root of that is 2, so you have 2 times root of 2gm over r. Okay, and this thing is escape velocity from Earth's surface. And how much is that? Escape velocity from Earth's surface, 11.2, right, kilometers per second. So therefore Vp would be equal to 2 multiplied by 11.2 kilometers per second, right? So it is 22.4 kilometers per second. That is the answer. Okay, so it is option B. Is this thing clear to everyone? Okay, very good.